Proxima Centauri, the closest stellar neighbor to our solar system, has long captivated astronomers. This faint red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite being only 4.24 light-years away, Proxima Centauri is invisible to the naked eye due to its low brightness. Yet, it holds tremendous scientific interest, especially as a host star of Proxima B, an exoplanet located within its habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and far longer-lived than stars like our Sun. Their dimness makes them difficult to observe, but also means that their habitable zones lie much closer to the star. In Proxima Centauri's case, this means Proxima B orbits at a distance of just 0.04856 astronomical units, a fraction of the distance between Earth and the Sun. However, this close orbit exposes a planet to intense stellar activity, including frequent solar flares and heightened radiation levels, creating conditions vastly different from those on Earth. The discovery of Proxima B was a major milestone in exoplanet research. Using the radial velocity method, astronomers detected minute wobbles in Proxima Centauri's position caused by the gravitational pull of an orbiting planet. These movements allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory confirmed Proxima B's existence, marking a pivotal moment in the search for habitable worlds beyond our solar system. Although ground-based telescopes have yielded important insights about Proxima B, they face considerable limitations. Earth's atmosphere distorts light and interferes with detailed observations of the planet's surface and atmosphere. Much of what we know, its mass, distance from the star, and orbit, is based on indirect measurements. To gain deeper insights into Proxima B's environment and its potential to support life, more advanced observational tools are essential. Instruments like the James Webb Space Telescope JWST are critical for this purpose. Proxima Centauri serves as an invaluable gateway to understanding planetary systems beyond our own. As the nearest star system to Earth, it offers an unprecedented opportunity to study the conditions that might support life. Proxima B, a rocky, Earth-sized planet possibly capable of holding liquid water, presents a tantalizing possibility. Yet its harsh environment poses difficult questions for scientists to unravel. The James Webb Space Telescope represents a monumental leap in astronomical capability. As the successor to the Hubble Space Telescope, JWST was designed to overcome many of Hubble's limitations and expand the frontiers of human knowledge. While Hubble revolutionized astronomy by observing visible and ultraviolet light, JWST is optimized for infrared wavelengths, allowing it to peer through cosmic dust and detect phenomena invisible to its predecessor. One of JWST's most significant design features is its primary mirror, spanning 6.5 meters, more than twice the size of Hubble's mirror. This enables JWST to gather far more light, making it sensitive enough to detect faint and distant objects. The mirror, coated in gold to improve infrared reflectivity, is made up of 18 hexagonal segments that work together as a single optical surface. Another key innovation is JWST's 5-layer sun shield, which keeps its instruments chilled to about -233 degrees Celsius. This ultra-cold environment is essential for capturing faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates at the second Lagrange point L2, a gravitationally stable spot approximately 1.5 million kilometers from Earth. This location minimizes interference from our planet's heat and light, allowing the telescope to perform continuous, uninterrupted observations. JWST's capabilities extend from studying the earliest galaxies to analyzing the atmospheres of exoplanets, like Proxima B. Its focus on infrared light is crucial for observing redshifted objects, distant phenomena whose light has been stretched to longer wavelengths as the universe expands. With state-of-the-art instruments, such as the near-infrared camera NIR-CAM, the mid-infrared instrument MIRI, and the near-infrared spectrograph NIR-SPEC, JWST is more than just a telescope. It is a time machine, a laboratory, and a testament to human ingenuity. Proxima B has captured the imagination of scientists and the public alike as a possible second Earth. Positioned within its star's habitable zone, it has the right conditions to potentially support liquid water, a vital ingredient for life. With a mass about 1.17 times that of Earth, it is likely a rocky planet similar in composition to our own. Its relatively close distance, just over 4 light-years away, makes it one of the most promising candidates for studying the potential for life beyond the solar system. However, Proxima B is far from a perfect Earth twin. Notably, it is believed to be tidally locked, meaning one side always faces its star in perpetual daylight, while the other remains in endless night. This creates stark temperature contrast between the two hemispheres. The terminator zone, where day transitions to night, may offer a narrow strip of more moderate temperatures that could support life. Despite these possibilities, Proxima B faces severe environmental challenges. Its host star is a flare-prone red dwarf, emitting powerful bursts of X-rays and ultraviolet radiation. Over time, these flares could erode the planet's atmosphere, leaving its surface vulnerable to the harshness of space. If Proxima B retains any atmosphere today, it would likely need a strong magnetic field to shield it from this radiation. Without such protection, the surface environment would be hostile to life as we understand it. Still, scientists remain hopeful. The planet's location in the habitable zone suggests liquid water could exist on its surface or beneath it. Life, if present, might have adapted to a harsh environment, similar to extremophiles on Earth, such as microbes that thrive in deep-sea hydrothermal vents or endure high radiation levels. Such life forms might survive through radiation resistance, subsurface habitats, or entirely novel biochemical processes. The search for life on Proxima B is more than a scientific quest. It is an effort to answer one of humanity's oldest and most profound questions. Are we alone in the universe? Proxima B stands as a beacon of that possibility, a rocky, Earth-like world that may harbor the right conditions for life. As our technology advances, so too does our ability to explore this distant world and unlock its secrets. Ultimately, Proxima B's environment is deeply shaped by the nature of its star. Proxima Centauri, unlike our Sun, is a small, cool, and dim red dwarf. Because of this, the habitable zone lies much closer in, pulling Proxima B into an orbit just 0.05 astronomical units from the star, roughly 20 times closer than Earth's distance from the Sun. This tight orbit creates unique challenges for the planet and any life it might support. Chief among these challenges is the star's intense stellar activity. Proxima Centauri unleashes powerful solar flares, bursts of energy that release large amounts of X-rays and ultraviolet radiation. Compared to our Sun, red dwarfs like Proxima Centauri produce these flares more frequently and with far greater intensity. Even if Proxima B possesses atmospheric layers, the planet faces significant challenges due to the intense radiation emitted by Proxima Centauri. High levels of ultraviolet radiation can break molecular bonds, preventing the formation of complex organic molecules, an essential step in the emergence of life. On Earth, hardy microorganisms like Deinococcus radiodurans have evolved mechanisms to repair radiation-induced DNA damage, suggesting that if life exists on Proxima B, it would need to develop similar or perhaps even more sophisticated adaptations. However, the level of radiation resistance required on Proxima B would likely demand biochemistry far beyond anything found on Earth. Interestingly, Proxima B's tidally locked state could provide certain advantages. While one side of the planet faces constant bombardment from stellar radiation, the perpetual night side could offer protective refuge. Subterranean environments, such as caves or deep planetary crusts, might shield potential life forms from harmful radiation. Likewise, if Proxima B contains underground oceans, they could serve as stable habitats, much like Earth's hydrothermal vent ecosystems that harbor resilient life deep beneath the sea. Despite these formidable obstacles, scientists are optimistic that Proxima B represents a unique opportunity to study how life might endure in extreme environments. Investigating how organisms could survive under such harsh conditions broadens our understanding of habitability and resilience beyond Earth. Proxima B is not only a potential candidate in the search for extraterrestrial life, but also a natural laboratory for exploring the limits of biological survival. Its proximity to Earth and location within its star's habitable zone make it an especially important target for ongoing research. With the development of next-generation space telescopes and instruments, astronomers are better equipped than ever to investigate this intriguing world. Although daunting challenges remain, Proxima B offers a fascinating glimpse into the kinds of life-supporting conditions that may exist throughout the galaxy. It reminds us that the quest to understand life's potential beyond Earth is still in its early stages. By closely studying planets like Proxima B, we expand our understanding of what environmental factors are necessary for life to emerge and thrive. One of the key reasons Proxima B garners so much interest is its Earth-like size and rocky composition, making it an excellent reference point for evaluating the habitability of planets orbiting other stars. Scientists are particularly focused on identifying exoplanets that resemble Earth, as these worlds are most likely to support biological processes. To further assess Proxima B's potential for life, astronomers are employing advanced techniques to examine its atmosphere and environmental conditions. A particularly promising method is transmission spectroscopy, which analyzes starlight as it passes through a planet's atmosphere during a transit. The way the atmosphere absorbs this light reveals its chemical composition. By studying absorption lines in the light spectrum, scientists can detect gases like oxygen, methane, and carbon dioxide, molecules closely associated with biological activity on Earth. Finding such gases in Proxima B's atmosphere would provide compelling evidence of life-supporting processes. At the same time, researchers are exploring the possibility of life existing beneath the planet's surface. The concept of subsurface life has gained traction, especially with the discovery of extremophiles on Earth that thrive in environments once thought inhospitable, such as deep-sea hydrothermal vents and highly acidic lakes. If Proxima B contains underground aquifers or water reserves, these could serve as safe havens, protecting life from the planet's harsh surface conditions. The existence of such environments would greatly enhance the possibility of finding microbial life adapted to extreme conditions, similar to those found in Earth's deep oceans. Beyond the search for life, Proxima B offers scientists a chance to push the boundaries of what we understand about life's resilience and adaptability. The exploration of Proxima B offers valuable insights into the forces that shape planetary systems. Positioned within the habitable zone of a red dwarf star, this exoplanet serves as a unique case study for examining how star-planet interactions influence atmospheres, climates, and magnetic fields, all critical factors in assessing a planet's potential to support life. For example, Proxima Centauri's powerful solar flares may significantly impact Proxima B's weather patterns and long-term atmospheric stability. By studying these effects, astronomers can better understand the broader conditions that govern habitability across various types of stellar systems. Although our knowledge of Proxima B is still developing, cutting-edge instruments like the James Webb Space Telescope are helping scientists uncover its secrets. With its advanced infrared capabilities, JWST allows for detailed investigations of the planet's atmosphere and surface, potentially providing the data needed to assess whether life could exist there. As the field of exoplanetary science advances, Proxima B will remain a key target in humanity's search to answer one of its oldest questions: are we alone in the universe? Importantly, the study of Proxima B goes beyond the search for alien life. It represents a deeper pursuit to understand the universal conditions that make a planet habitable. By identifying these factors, we can better focus our search for life-sustaining worlds elsewhere in the cosmos. Proxima B is just one chapter in our ongoing exploration of the universe beyond our solar system. Its study also sheds light on planetary formation and stellar evolution, particularly in red dwarf systems. By examining the dynamic relationship between Proxima B and its host star, scientists gain a clearer understanding of the forces shaping closely orbiting planets and their development over time.